What's up, everybody? Welcome to lecture 12. Today we're going to be talking about section 2.6. I thought before we got into that material, we'd start today off with an example problem from the last section. No, do not turn off that computer. No. It's not going to be that bad, I promise. I promise, it won't. Stick around. I'm going to give you all a couple of seconds to think about this, though. How would you go about finding the derivative of that thing? No, do not turn off the YouTube channel. Think about it. Don't speed it up either. Well, there's a trick here we could apply that I think might help. If I remember correctly, and I always do, we could rewrite this as e raised to the ln of b, right? And all of that raised to the x power. Which that is just the same thing as e raised to the x times the ln of b. Okay, that gets us going. Because now, that thing I can take the derivative of, right? If this is about the last lecture's material, then I need to identify an inside function, f of u, or an outside function, f of u, let's call that e to the u, and an inside function, let's call that g of x, and it's going to be equal to x times the ln of b. Now the question is, what are the derivatives? Well, the derivative of e to the u is just e to the u. Oh, okay, cool. d du of e to the u is equal to e to the u, dope, that's out of the way. And the derivative of the inside function, well, it's just x times a constant, so it's just that constant, right? Yeah, absolutely. X times the ln of b. The derivative of x times the ln of b is just the ln of b. For anybody who logarithms are rusty for, again, I would suggest you go check out the algebra notes. Logarithms are towards the second half, around 3/4 of the way into those notes, I think. I won't swear to it. But this problem, we've got the big stuff out of the way, right? The big parts of it. Because now we just have to multiply these two results together to find out what the derivative of that original function is. So, dx of e raised to the x is equal to du of e raised to the u times dx of x times the ln of b, which we now know to be e to the u times the ln of b, or plugging everything back in and rearranging a little bit, we get the ln of b times e to the x times the ln of b, which we can rewrite as the ln of b times b raised to the x. And that's it. That's all she wrote. Having said that, let's get on with the material from this section. Cool. All right, so this section is all about what's called implicit differentiation. So before we get into that, we're going to need to go over some vocab. In particular, we're going to need to talk about what's called an implicit equation. An implicit equation is an equation that you just can't separate x and y. Like, there's no way to untangle them nice and neatly into one equation that describes the entire system. As an example of that, I give you Exhibit A. Well, Matt, you might say, we could do that. We could rearrange this equation and separate x from y. Okay, let's check it out. So this tells us that y squared is equal to 9 minus x squared. And if we took the square root of both sides, we get that y is equal to plus or minus the square root of 9 minus x squared. Aha, you say. See, I told you so. We could untangle those. And I say to you, no, we can't. Look at what you've done. You have two equations here, right? This thing is equal to the square root of 9 minus x squared and negative square root of 9 minus x squared. And you say, okay, well, that's cheating. And I say, no, it's not. These are two different equations, aren't they? This equation describes the top half of this circle centered on the origin with a radius of 3. And this equation down here represents the bottom half of that, right? So you can't actually untangle these x and these y's from each other and describe the entire system. Sure, we can describe parts of the system, but not the entire system. And that's what an implicit equation is. It's an equation that x and y are just so tightly bound together that it's not enough to describe the entire system with one equation. That is just written in terms of x, or just written in terms of y. No, no, no. Have to have multiple equations. Or you could just have one equation that uses a bunch of x's and a bunch of y's all mounted together. You tell me, okay, so what? I don't care, Matt. Like, what good is this? I say, well, this is a nice example, but imagine I ask you to do the derivative of both of those. And you say, oh, okay. Well, this is a nice example because the derivatives are going to be the same, just one's going to be negative of the other one. So, whatever, Matt. So, sure, okay, you got me there. This case is an easy case. But there are cases that aren't easy. For example, maybe you have xy squared is equal to cosine of x over y squared minus x. I don't know. Something ugly. This is brutal. Brutal, I say. Brutal. I don't know how to separate those. Like, I'm being genuinely honest right now. I don't see a method to separate any of those. Like, you're always going to have x and y kind of intermixed with each other. There might be one or two tricks here, but none are coming to mind right away. So I come back to this previous example and I say, okay, so this thing, being able to identify these types of functions, it's going to be helpful because you're not always going to be able to necessarily break it up like this. Like I said, here, I don't see a way to do that. But I might need to know what the derivatives are of this thing at a particular point. To which you look at this over here and you say, oh, hell no. And so that's all right. We're going to work with this one. This one is going to be our example first. And what it's going to be an example for is what's called implicit differentiation. Implicit differentiation is the differentiation process we apply to implicit equations. And all it does is it assumes that y can be written as a function of x. We kind of use a dummy variable idea. Again, it's actually very, very much a chain rule sort of process. In fact, we used it in the last lecture. The way it works is we're going to say, all right, I want to apply the derivative to this equation. That means I need to apply d dx to both sides. But first, we're going to make an assumption. We're going to assume y is equal to f of x. I'm just going to make that assumption for right now. It's just some arbitrary function with respect to x. And that's going to tell us that dy dx is equal to f prime of x. And we're just going to leave it at this notion for right now. We don't actually care what dy dx is or what f prime of x is yet. Now, with this in mind, what we are going to do to apply, or to use implicit differentiation is to apply d dx to both sides of this equation. We're going to take d dx of x squared plus y squared. That whole thing is equal to d dx of 9, to which you say, hey, that right side's easy, I know that one, that's 0. I say, you are correct. This is equal to 0 on the right-hand side. But on the left-hand side, we need to apply that derivative to each individual term. So this is going to be d dx of x squared plus d dx of y squared. Okay. That first term is kind of straightforward, right? That first term, d dx of x squared, well, it's just going to come out to be 2x, isn't it? So rewriting everything over here, because I hate that feeling of my instructor being a squirrel, writing all over the board and nothing being organized. Actually, carry that on over the top. This first derivative is just going to be 2 to the x, or I mean 2 times x. And the second derivative, well, the second derivative is of a function squared. A function squared. You know, it sounds like the chain rule, doesn't it? Yeah, because it's a function inside of another function. It's f of x inside of the function u squared. So f of x is equal to u. And you're squaring u. Just think of it that way. Okay, well, in that case, this should be 2y times, excuse me, dy dx, whatever the derivative of y is. And all of this, again, is equal to 0. Well, I can kind of isolate the y's from everything else, right? Like I can kind of isolate x from everything or the y's from everything. I can do that by saying, this then tells us that 2y dy dx is equal to 2x. And you know what? If I were to divide both sides by 2y, I could just get dy dx on its own. So this then tells me that dy dx is equal to, I forgot a negative sign in here, it's equal to negative x over y. I just forgot the negative sign here. Fixed it though. So dy dx is equal to negative x over y. That means if I want to know the derivative of the equation x squared plus y squared equal to 9 at a particular point, all I need to know is what that point is. And I can plug in x and I can plug in y and can get that derivative back. That's nice. That's really nice. Like, unbelievably convenient. And I encourage you to play with it. Give it a try. Take some derivatives, or take some points that you know, and plug them in. And then compare them to the derivatives of that piecewise solution we had. The piece for the top and the piece for the bottom. Having said that, let's keep moving on. Let's check out some more problems. All right, so I am literally going to lift this example problem right out of your lecture notes. This example problem wants you to find the line tangent to what is called the folium of Descartes at the point 3, 3. Okay, so what we need to do here is find the line tangent to that equation at a particular point. Well, thinking back to all the stuff we heard about tangent lines, that means we need to find the equation y minus, we're going to use the point 3, 3, so we know y naught and x naught. They're going to be 3, 3. So we're going to find the line y minus 3 is equal to dy dx at the point 3, 3 times x minus 3. Now these 3's are coming from the point, and what I am saying here is we want the derivative of this thing at that point, right? So just a heads up on some notation. I sometimes use this bar with some information down at the bottom of the bar just to tell you what's going on. So here we're saying you want the derivative of this, of y with respect to x, at the point 3, 3. Okay. So that means we need to find out what dy dx is. That means we need to take the implicit derivative of that. Okay. If that's the case, then all we really need to do is apply the derivative to both sides, apply chain rule, and do some rearranging of terms. So let's do that. So we've got d dx of x cubed plus y cubed is equal to d dx of 6xy and we look at this for a second, we say, okay, I can split this one up, I can pull this 6 out, and I can apply the product rule. We're going to do this all in bits and pieces though. First we're going to split this up and pull that 6 out. I'm going to choose a different color so things don't get confusing. So we have d dx of x cubed plus d dx of y cubed. That's the sum and difference rule, right? Now we're going to pull out this 6. 6 times d dx of xy. That's the product rule, the constant multiple rule. And now we can apply the power rule to both of those, the chain rule here, and the product rule here, right? So power, simple power rule here, the general power rule here, and then the product rule here. For those who aren't sure what I'm talking about when I talk about the difference between the simple power rule and the general power rule, the difference is the general power rule uses chain rule. The simple power rule doesn't. So, doing all of this, what we're going to get is that this is equal to 3x squared plus 3y squared dy dx is equal to 6 times, well, we need to take the derivative of x first, so that's going to be y times dx dx, which is just going to be 1, plus x times the derivative of y, which is dy dx, cool. Now we can start simplifying some things. First, we can distribute that 6 all the way through and try to get all of our dy's on one side. So doing some of this work, actually, before we do anything else, let's get rid of these 3's hidden inside of this. So we're going to divide everything by 3 just to simplify some of the work. This is going to be x squared plus y squared dy dx is equal to 2 times y. Well, dx, the derivative of x with respect to x is just 1, so nothing happens there. It's just y plus x dy dx. Now we can distribute that 2 all the way through, this 2 right here. We get that this is equal to x squared plus y squared dy dx is equal to 2y plus 2x dy dx. And from here, we want to try and get everything with a y isolated on, everything with a dy dx isolated to one side, and everything that doesn't have a dy dx isolated, to the other side. So what that's going to look like, we should have arrows all the way through. So what that's going to end up looking like is going to be x squared minus 2y is equal to 2x dy dx minus y squared dy dx. Okay. Now we can pull out that dy dx and start grouping everything, right? So what I mean to say is, now we have x squared minus 2y is equal to the quantity 2x minus y squared times dy dx. Hey, check it out. We could, if we wanted to, divide out 2x minus y squared from both sides to get dy dx. So all of this tells us then that dy dx is equal to x squared minus 2y divided by 2x minus y squared. Well, if that's the case, then dy dx at the point 3 comma 3 is going to be equal to 3 squared, so just 9, minus 2 times 3 is 6. So let me actually write all of this out. The quantity 3 squared minus 2 times 3, all divided by 2 times 3 minus 3 squared. Well, hey, that's negative 1. So coming back over to here then, this is going to be y minus 3 is equal to negative x minus 3, which gives us then, since we can distribute this negative all the way through, it gives us that this is going to be equal to, or this is going to give us that y is equal to just negative x. My mistake. Negative x plus 6. I apologize. Negative x plus 6 is what that gives us. Whew. So what the hell did we just do? Let's review this entire problem, because there was a lot going on. First, we're told we want to find the line tangent to an equation at a particular point. And we said, okay, well, I know I can put this all in point-slope form. That's what's in blue right here. Where the points, y, or x naught, y naught, is just the given point, right? That's 3, 3 here. And the slope is the derivative of our equation. That's what's in pink up here at that particular point, at that given point. Okay? So I can set up the problem, right? I can set up the point slope form pretty easily. I just have to figure out what dy dx is. And then I have to find out what dy dx is at that point, 3, 3. So we apply implicit differentiation. And after working it out, we get all the way down to here, right? And we say, haha, this thing will allow me to solve for dy dx. And once I do that, I get an equation that tells me what dy dx is in terms of x and y. And luckily, I know what my x and y points are. It's 3, 3, right? And because I know that, that means I can find out what dy dx is at that point. It's negative 1. And I can plug it back into this. And after I work it all out, I find that y, after I work it all out and get it back into slope-intercept form, or rather, get the tangent line in slope-intercept form, I find that y is equal to negative x plus 6. And that's it. That's all I've got for y'all on this one. Implicit differentiation, by and large, just comes down to pulling back for a second and saying, all right, I'm not going to think of y as y. It's implicitly going to be understood to be some equation in terms of x. I just don't know what that equation is. And that's going to let me take the derivative using the chain rule. And then after I do that, I'm going to work all the way down until I can solve for dy dx. Then I'm going to use that to do whatever I do. But again, having said all of this, that is all I've got for y'all in this lecture. Have a good rest of your day. Later, guys.